So welcome back, everybody, for this afternoon session. So we will start with Rosa Poggiani talking about electromagnetic observation of supernovae for gravitational wave searches. Thank you, Rosa. Take it away.
Thank you, Matteo. Hello, everyone. I will, in this presentation, I want to give you the perspective of gravitational astronomer when dealing with electromagnetic observation of supernovae, mainly optical observations. Basically, from the point of view of detection, the LIGO-Virgo-Kappa collaboration are interested in close collapse supernovae that are as far as 30 or 40 megaparsec, more or less. What we will see is that during the LIGO-Virgo-Kappa runs, there have been different supernovae covering basically all the types we're interested in, 1b, 1c, 2. And of course, with supernova, we are in an opposite position with respect to the mergers. For the mergers, you have a large localization region, and then follow-up is starting. Here, you have plenty of information, electromagnetic and neutrinos, precise sky localization. And of course, in addition to providing information about the supernova mechanism, gravitational observation can be very, very useful. By the way, optical observation, electromagnetic observation triggers our observation and analysis. And the key point is the multiband photometry that we will use to narrow the gravitational wave search region. Of course, there are some related problems that has been addressed by observational theoretical work at this conference. One is the estimate of progenitor mass, which is related to the time of shock breakout. Then for our analysis, not only there is the problem of choosing a suitable distance for the host galaxy, and that there are also supernovae that do not show the plane, rise to maximum, and then decline with or without plateau. Basically, from the statistic point of view, if you access the Rochester supernova archive, you discover that there are a large number of objects that could fill a supernova or transient. Sometimes they are luminous blue variable, sometimes they are nova. But by the way, you see the effect with the phase transition around year 2015, when a large part of the sky service is operating. And you see that if you want to dig the transient, you are live the recent year to have more than 20,000 transients. Of course, not all of them will be of interest for us, but you see there is a key take-home message. The most part of thin transients is not classified. There is not the typing of the supernova, and this also holds for close supernova sometimes. And this is a problem. We are missing a part of the population, basically. Of course, some objects are very faint in very distant galaxies. There is a good reason probably because there is no coverage. And so, from the optical point of view, we are interested to get the wall light curve, at least the first detection, and also the last non-detection. And this depends on the limiting magnitude of the instrument you use. And this is a selection of approximate limiting magnitudes of those sky stars that are more frequently found in our work. You see, the telescope in this survey are not big ones, 4-meter telescope. They are doing an efficient job of monitoring the sky survey. And you see the leading magnitudes range from 17 to about 21. Of course, the limiting magnitude is a key point just to understand when you call it a detection. A detection with a larger telescope could be earlier because we are able to go to deeper magnitudes. And also what is how to compare the non-detection. And in addition, you have to check how large is the photometric error. If a supernova is faint, maybe you accept a point with large errors to build the curve or not. There are a lot of choices involved. And just to remind quickly that the core collapse supernova for a gravitational astronomer, there is a common point. These are typical light curves. There is an universal shape up to the peak. So there is a rise in time, but not full of them. And then a different way to undergo the decline. There is a plateau. There is the rise to maximum can be larger, can be longer, and so on. And of course, there is spectroscopy. Of course, this is a universe and the textbook in its own. Basically, for us, spectroscopy is important for classification. And of course, it's of paramount importance to understand how a supernova is evolving, how it's interacting with the environment, and so on. Basically, there is a recent paper just focusing on building a complete catalog of close supernova within 40 megaparsec. And this author surveyed the sample of supernova from 2016 to 2023, and they discovered more than 200 supernova, and among them, about 100 are supernova type 2, and about 30 are type 1b and type 1c. Of course, they made a lot of analysis and investigation, and for example, corrected the volume linear sample for the magnitude bias, and the pie chart, you will see the percent of supernova 1bc and supernova 2, just to have an idea what to expect. Basically, 1c and 2p are winning in the two cases. They also addressed the host galaxies. And in the top part, you see that there is the statistic of the galaxy of the hosting the sample they analyze. In the bottom, there is the glide plus sample. And you see that from the point of view of the sample statistic, the SC galaxy, spiral, this kind of galaxies are favored. On the other end, the glide plus sample favors also the right side, especially the irregulars. And this is a point to be addressed. Of course, I will not repeat what Michele Zanolissen said, how we are measuring, how we are narrowing the gravitational research. I remind you there are basically two ways. Looking for early photometry and collecting the non-detections and the initial part of the light curve, or doing extrapolation, and so interpolation, typically at the quartic interpolation. And you see that both methods can be used in the searches during one or two runs and the 3 searches. And I just want to remind you what we have presented, the statistic of supernova that has been investigated by LIGO, Virgo, Cagra. During the 1 or 2 runs, the focus was on 5 supernova. You see 4 type of P and 1 type 1b bar C. Basically, what I show you, what was not possible to prepare at that time because the work was at the time that you had much less data. Just showing you that these are the light curves of a sample of the supernova in the previous slide, showing you that even in the first 2 runs, showing you access to different kind of collapse supernova. And then there is the O3 runs, which much improve sensitivity. And you see that here you get 8 supernovae. And you see that there is a large spread in the kind of supernova, 2b, 2, 2p, and 2b. And again, I show you how, these are just examples. You see you have supernova with a traditional shape, supernova with double peak, plateau supernova, and so on. So basically, gravitational investigation not investigated a simple type of core collapse supernova, but a broad range. And just for documentation, I just report here the tables. Yan presented the collection of supernovae, with good coverage. I tell you that it is not a commitment that, as Marco was saying, that we analyze all of them, but we are keeping track of all of them, especially if they are peculiar. And you see that the O4 run, if you just accept supernova up to 40 megaparsec, there are almost 10 supernova in O4A run, with different morphologies, I say. And again, we have also 1b and two family type supernova. And if you look at the supernova occurring during O4B run, I need 2 pages. This again just for documentation. And again, you see that during this run, you will find different kind of supernovae of type 2, and also 1C1. So we have plenty of them in the 4 run just to explore the core collapse supernova. And of course, what we can say, the photometric coverage is not good or complete for all of them. There are some supernova that are faint that have not such good coverage at a few points and so on. But you see, if you accept to go up to 40 megaparsec, there are a lot of possible targets. And again, some supernovae in this sample are bright. And this is a famous example. I just remind what Yayan presented about the upper limits about the supernova to remind that this is a real multi-message object. You see, this is a multi-band light curve during the initial stage with some points marked. Just at the beginning, these objects, the supernova, has been observed both in the X-rays and in the radio. And also there are upper limits from gamma ray, from Fermi-Lat, and from a neutrino experiment. And you see the search window in this year was easy, as Jan was saying. This is a sample of the supernovae that you can measure during the O4 run. You see that in all these graphs, the downward face is triangle. It was his official last non-detection. And the rest are multi-band light curves with the Atlas OC curves, ASAS data, and so on. You see, for this example, the coverage is very good. And there is another supernova which is of great interest. 2024 GGI is as close as 2023 IXF, and the photometric and spectroscopic evolution is very similar. So it's a very interesting object. And there is also the ISS with this kind of double peak and so on, which is, you see, it's quite bright. So this is the reason why it is very well observed. And then there are strange objects. 2023 FYQ. This is a supernova which has the right part very classic, rise to maximum, then so on. And then there is a slow rise to the final rise by chance. The interesting part just fall inside the O4A run. And the interpretation of the paper is that the explosion occurs when there is the change of regime. And so I have a question for you. How could we describe the effect of the slow rise to the explosion and to what happened afterwards? And there is an object like 2024 XUO. For example, there is a bump, you see, a precursor bump before a very normal evolution. And there is 2024 AECX. Again, there is this kind of spike, a precursor. And so these are two objects. I ask you how it is possible I would like to discuss possible models for this kind of object and how they impact on the gravitational waves. And for the FYQ, there has been some modeling just to explain what's happening, including the very interesting possibility that this is a cork-collapse supernova hosting a binary system. One object could be a very compact object. So this is relevant for gravitational wave from a lot of points of view. And by the way, precursor emission is not rare. Let's think about 2009 IP and so on. Also, we have a problem. Some interesting supernova are missing maximum. So another point of discussion would be, are we able to have a template just to reconstruct this kind of objects, just to find the maximum and surroundings? And then what Michele was saying, please give us a progenitor mass and we'll extract the time for shock breakout. So look at the distribution of mass estimates for 2023 IXF. There are two kinds of estimates, explosion imaging and light curves and modeling and so on. Basically, you cover everything from 8 to 24 solar masses, and there is not even agreement between the same classes of method. So this is a problem that, it's related to the choice stellar motion simulation, but I ask you to discuss this point in detail. How could be some guidelines for the progenitor mass estimate? And there is another point, and this is a philosophical point, the distance of the host galaxy. There are hundreds of methods to measure the astronomical distance. And here I propose you the distance of M101, the host of 2023 IXF. You just get from net extragalactic, you just plot, you just split by the different kinds of methods, and you find there is a large spread, and sometimes the error is missing. So at the end, in our paper about the supernova, we decided to take the median. But if you plot the histogram, there is this problem. It's even bimodal. And if you try to put to build the histogram a different method, there is the discussion. So I would like to open a discussion about this point. If, for example, we have to choose C fades, because they are the best or something like that. And I tell you, if you go to Rochester, sometimes the redshift is not consistent with the no-redshift distance. So my conclusion are that, of course, this is a very interesting field as gravitational astronomers. We are watching and getting the result from the electromagnetic community. Of course, I would be happy if more this transient could be supernova could be classified, but this is a big effort. And of course, I would like to ask for a good photometric coverage for every supernova, but this is uneven. Depends on the weather, depends on the fineness of the object. And I have to set conclusion that I have to go through in depth to estimate the mass of the progenitor, and also to understand which is the best distance to choose, and so on. And just seeing, you see, we have explored, we continue to explore these families of core collapse supernova. Thank you for your attention.
Thank you, Rosa. Thank you. So, questions?
Thank you very much for a nice talk. So as you mentioned, if about 50% of supernovae are unclassified, but we probably also know its host galaxy, right? So should LVK also explore this unclassified supernovae within some distance?
You mean this graph?
Yes.
Yes. Basically, to date, if it is not classified, we do not start. We do not follow it. Of course, we check in the weeks after for if classification allows. It's not a problem. Sometimes you discover this classified, let's say, 2 weeks afterwards. Or for example, the 2024 XUO was peculiar. At the beginning, it was something with a BANCP. So it was classified with something else, and then decided to behave as a supernova. So there is a key point, just to watch what's happening, but it's not obvious to have a spectroscopic classification, unless probably there is a joint agreement, and this for all of us, electromagnetic and gravitational, that, you know, to make this effort. But no, so far, unclassified are not followed. We check if they stop being unclassified.
So, Jade, but before that, if Tango could approach the desks, especially if he has the to branch the laptop, then Jade, please, a question.
Rosa, I think you've been doing an excellent job at finding supernova candidates for us to search for. So I just wanted to say a big thank you, because that's like a really big effort that's really useful for everyone. So my question is, so these are all kind of like regular supernovae. So do you think we could also look for things like maybe that could be like really extreme supernovae, like some long gamma ray bursts, or maybe something that's between like a regular supernova and a disappearing red supergiant, so like some kind of faint electromagnetic transient that could be a failed supernova?
Oh yes, Jade, I agree with you. It would be very important, since we are at the beginning of this astronomy, gravitational astronomy, to be open to everything. So I would be strongly in favor of adding Phyla supernova and all the objects you are mentioning. Basically, we don't know, if we will have a surprise with this kind of sources, you know. And so, of course, just following and also interact more deeply about modeling and observation. Thank you.
Any other question? We have still 1 minute. I wanted to ask you, maybe I lost it. How many type 1c were looked for in the different runs? Like you showed 04, I think you had a bunch, or 03?
8, 02, 102 were 8, 03 were around 10, and there were more than 20. And I left for C, follow in the sense that we
Type 1c? Supernova?
Of our C, I have not.
No, the type of the supernova.
Yeah.
Like
How many?
and how many of the type 1C or 1B?
Mostly 404 type 2 indifferent incarnation, a couple are 1C, more or less. Also in the O2, O1, O2, and O3, there was a type 1C for each case, and there were 2 404. So.
Okay, thank you. So if there is no further, yeah, great. No, okay. So very quick questions.
So you did have one, this is following on his question, Matteo's question. You had one broadline 1C that was in NGC 681, so like 20 megaparsecs away. What kind of constraints do we place on the, can we place some strong or even weak constraints on the signal that may constrain the rotation at all? Or is it just not good enough?
I would be more on the side of detection. Up to 20 megaparsec, I think that you can, it could be, I think you could set tight constraints. By the way, you see, to have the tightest constraint so far, you have to be so lucky to have 2023 IXF, just less than 7 megaparsec distance. So I think that probably there will be first a stage of detections, and then probably a discussion with the supernova community, just try to understand, that we consider a variety of models and so on, and we are waiting for new models. So unless they are extreme modes so far, it's difficult unless there is a galactic supernova. But there are a lot of supernovas, so it's worth it just following them, putting upper limits, and so on.
Extremely quick question with an extremely quick answer.
I hope that the answer, maybe the answer was already given. I apologize, having been late. We had an intense discussion or a lively discussion over lunch. Maybe you had given the answer in your talk, which I didn't follow. Why is the classification of most cases not possible? Didn't people apply machine learning techniques to do that? Is there a possibility to actually get these classified?
Technically, the most part of the supernova I was showing, they are discovered by Rossky surveys. That are photometric surveys. And a few of them have been discovered by Takagi, who is a very prolific discoverer of supernova. But generally, there is an announcement on the transient time server and so on, and the supernova Rochester and so on. But I've seen that unless it is peculiar as the IXF, of course, seldom there is this effort. Sometimes when there is a supernova announcement, something at magnitude 19, so you must have quite a large aperture telescope. You cannot do it 30 centimeters. So I think this is one of the reasons that less people is interested in supernova and to build a coherent sample, the region close to maximum is missing, so there is no classification. By the way, I know there are people just doing surveys, but this thing probably you have to be there just on the spot.
Okay, let's thank Rosa again.
Thank you.